Hello, my name is Sloane Tribble, and I am going to share my final parallel program for CSCI 551, spring of 2024, with Dr. Sam Seward. Now, this program is designed to take in an image and divide it into a grid of a given size, and rotate it by a given angle of rotation, counterclockwise. And this is implemented in both sequential and parallel fashion. So let's see here. Let's go ahead and start just by doing a clean build. Alrighty, so we are building. Okay, so there's the first thing that could be kind of interesting is we have this -03 flag passed into our make file, and this is going to perform some more aggressive optimizations, which will hopefully help with speed up for OpenMP in our parallel program. Now, this will lead to longer compilation time and sometimes larger executable size and bugs. And some features of what it actually does include converting function calls into just their actual function code, also known as inlining, and then multiple iterations of loops will just be unrolled into a single iteration. And just for fun, let's just see if this actually affects the compile time, because we saw that took a minute there. Big clean, big. So, I mean, I don't know, I didn't really see any difference in compile time, but to be fair, it's a pretty small program. Anyway, let's just keep it as it is, because I know that this will actually work with the -03. I never tried it. I didn't verify it as thoroughly with the other flags. So, anyway, our code has been built and it is ready to roll. So let's go ahead and run our programs, Kaleidoscope, OMP, and note that for this OpenMP solution, it's actually slower for the grid size of such a small grid size, but we start to see some benefits as our grid size increases. So what just happened is that our programs were passed this input image here, which just for easy visualization has been already divided into a 2x2 grid. And then we have the sequential output. This is just a different zoom size. It has not actually been translated. It has not been increased in size. But anyway, so as you can see, each cell has been rotated. And then we can see the exact same output generated by our parallel version. And with that, I believe we're ready to actually look into some code. Since all of the timing and everything is covered in the write-up, I'm not going to go into that now. So, this code is based on a long and arduous conversation with ChatGPT-4, essentially asking it for a custom program that could be easily made parallel that would perform some interesting effects on an image. Now, as you might expect, GPT-4 didn't initially produce something particularly useful, but after much coaxing and then some personal tweaking on my part, I was able to end up with this sequential program. So what it does is makes use of this OpenCV library to work with an affine transformation matrix and just perform all kinds of nice, handy operations on images with that matrix. Now, let's see, we're also making use of the chrono library for, high-resolution time tracking. It's also worth noting that this program will segfault if the grid size is much larger than 600. I think that's something to do with the calculations performed within the library needing cells to be a minimum size. It could also have something to do with some odd side effects within this generated code. But 600 by 600 is pretty good for an image like this, so I was happy with it. I think it still makes some neat effects. And hey, speaking of which, let's just see what it looks like if you do, say, 600 by 600 with an angle of 45. And we will see Ooh. Oh, I see. That's probably because of all the little borders surrounding it. So, yeah, I think that's because of each of the little borders surrounding it that we end up with it looking kind of dim. There's probably just a lot of black surrounding each of these pixels. That's how I make sense of it. But let's see. Let's do 200 by 200. Make. Okay, there we go. So that's more what I would expect to see. You can see that each little cell has been rotated 45 degrees. All these little guys. Kind of cool. Anyway, that's what it does. And here's how it does it. Mainly through this rotate image part function, which is going to take in OpenCV matrix object reference called image part and then an angle. And with that, it is going to use the columns and rows for that image part, determine the center of that using floating point division, assuming that the image part object has an even number of rows and columns. It's going to generate a 2x3 affine transformation matrix, where the center object from above is used as the center of rotation, and then it's going to do the rotation and scaling specified as macros. Oh yeah, well, and this one is passed in. Well, anyway, let's see here, and then we're going to calculate a bounded rectangle to contain the image part once it's rotated, because as you hopefully can, I'm sure you can imagine, if you have a square that you're rotating 45 degrees, it's going to have these corners that would poke out of that original containing square. So we need to make a bigger square to contain that image no matter what angle it's been rotated to. And that creates this new object bounding box. And we want to also ensure that our rotated image is remaining properly centered within that bounding box. So we access the first row, we access the translation component along the x-axis for our transformation matrix. We calculate the difference between the center of the bounding box and the center of the original image along the x-axis, and we add this to the translation component to align the center with that of the original unrotated part. And we do this for the x and the y-axis. We create a new matrix object to store the rotated image part, and we use this warp affine function to do the desired translations, making use of that affine matrix that we have just generated up here. This rot mat is passed here as a rotation matrix. And with that, we have mostly covered everything, but there's still some more. So we are using the chrono library for this clock, and we're starting things right at the very beginning of the program. We're going to load that input image, again making use of OpenCV. We're loading it right into the matrix type. Allows us to easily iterate over it. We're going to crop the image to make it square. So for reference, we were originally dealing with an image. I had this as my starting image, and rotating every cell in this, dividing this into a properly sized grid would be a lot tougher than just using a square. So just to keep things a little simpler, we got the square. Now, that is accomplished by determining the minimum dimension of the input image. Is it horizontal or vertical? And then that is used to determine the square dimension. And then we also just extract the square image from the original. Oh, and the region is based on the center of that original image. So we initialize a result image as a matrix of zeros, making sure that it has the proper size based on our square image, columns and rows type, and a scaling factor that we may have determined. We're going to calculate this offset, which is going to be used within our loop here, our nested loop. So we'll get back to that momentarily. This is basically just to ensure that we are keeping each translated image in the center of where it began. So now we have this nested loop where we are iterating through our image, our input image, based on this grid size. we're going to calculate the region of that image that we're going to transform for this particular iteration. And we're going to generate another matrix object to represent that just specific part of the image. One interesting thing was that you could also easily do variations on the rotation angle here to have a little bit kind of different visual effect if you want, just to add a little more practical value to this program. And then we're going to just pass that little region, that matrix, right into our function. And once we have that, we're going to determine the center of the grid cell in the result image where we want to actually put this rotated part. And then we want to ensure that what we have just calculated is within the bounds of the result image. So if any of these dimensions are negative, they're going to just be zeroed. And we're going to choose the smaller dimension of the two. Oh, let's see here. I don't know about that last part, actually. But this is essentially to prevent any out-of-bounds issues which could lead to seg faults or other bugs. Additional error handling for cells with negative dimensions, which could just be a side effect of the library. And then here's the subregion, the larger output image. So this is the destination where we want to put our rotated part. And then we have this mask that we use to determine how much of this source image we want to copy to the destination. And we're just using a matrix of ones with the size of our rotated part, and we're using this single channel binary mask, and we're always just going to multiply it by 255. So to my understanding, the single channel mask is good for performance efficiency. We know that we're always going to want to just copy the entire image, so we do not need a more complex mask. So we use the simplest possible. And then we make that copy, and that's essentially what we do for every cell that we have calculated, and that's how we get our resulting image, which we which we output here. We save as an image, again using this nice CV library. Calculate the total cells just for output to help the user understand what in the world just happened, and then just let them know how long it took. And then just worth mentioning that the duration is expressed in milliseconds here and stored as a double for easy calculations and output. And then otherwise we have this OpenMP parallel version, which as per the write-up generated some really great results. It generated some really good speed up. And all it took was this. We have a little bit of code here for debugging, which is just going to start a parallel region, and then for one single thread, it's going to have it output the number of threads being used by the entire program. And since I'm not specifying it anywhere else, you can specify it as an environment variable, or if it doesn't find it, it's just, if the program doesn't find that environment variable to have a value, it's going to just use as many threads as it can, which in this case would be 12. As we can see evidenced a moment ago when we ran our code. No environment variables, and this processor, my computer has 12 threads, 12 CPUs, virtual CPUs, so that's what we got here. Anyway, where's that line of code? There it is. Alright, so this is all we needed. This Pragma OpenMP Parallel 4. And this allows each of these iterations to be passed to a different thread. And in order to try and optimize on this a little bit more, I tried this collapse clause to collapse each of these two nested loops into a single loop to create a single iterable space for each of these threads to act upon. And if I understand correctly, this could add some good speed up if our outer loop, for example, had a lot fewer iterations than the inner. Then that would help to more evenly distribute that work among each of these threads. But since here the inner and the outer loop are of the same size, I did not see any kind of benefit to this, so I just left it out. The only other thing to really mention is that I did experiment with having some extra visual effects, but just wasn't able to. I just didn't think they were really worth the effort. Not worth the effort. I mean, they did what they just didn't do much. That's all I'm saying. So, anyway, let's see here. With that, we have ourselves a working program. I hope you enjoy going through this and looking back at the comments, and hopefully find a lot of value in this presentation. So thanks so much for your time, and all the best.